All right, so now let's talk about the method of isolation. So far, we've talked about rate laws that are very simple. It depends only on the concentration of one reactant. In general, the rate of a reaction will depend on the concentration of more than just one reactant. But because it's very easy to deal with rate laws that just involves one reactant, we do a trick here called the method of isolation. What you do in the method of isolation is you use excess reactants. All the reactants you're using, you use excess except for the one you want to study. Okay? So let's say you might see something like this in the lab. You have a reaction between a dye and sodium hydroxide. So your hydroxide ions will react with the dye. You might set up that experiment so that the concentration of the dye initially is very low, so like 0.0001. Okay? And then you have a large excess of your hydroxide. Let's say you use 1 molar solution of sodium hydroxide. Okay? Throughout the reaction, we say then that, okay, let's imagine that the reaction is completed. Okay? How much of, what would be your final concentration of hydroxide? Let's say you lost all of this dye. And let's say it's a 1-to-1 ratio for the stoichiometry. How much sodium hydroxide would you have lost? Same amount, right? So you would end up for the final sodium hydroxide solution, if the reaction were to go all the way, you'd have the starting amount minus the amount you've lost, which is 0.0001. What is 1.00 minus 0.0001? 1.00 minus 0.0001. Yeah, but using sig figs, it's still 1.00, right? It's like saying you took a drop out of the bucket. It's still a bucket left, right? So, in other words, throughout most of the reaction, the concentration of your hydroxide will be essentially constant. So you use a large excess of one of the reactants. In this case, your final sodium hydroxide will still be the same as your initial. Okay? Now let's examine the rate law. What happens to the rate law if that's the case? Rate equals some constant K, your rate constant, right? Times hydroxide raised to some power, correct? Times the concentration of the dye raised to the order of reaction with respect to the dye. But since throughout most of the reaction, the concentration of hydroxide essentially remains unchanged, you can lump this hydroxide concentration raised to the power x along with K into what we would call an apparent rate constant. So this will replace that with another constant. So the APP there means apparent. So that's your apparent rate constant. So that expression right there is apparently constant. So we replace that by K subscript APP. That means apparent rate constant. Okay, so now you've simplified your rate law. Now your rate law, according to this, will just depend on the concentration of the dye. So you run an experiment where you just monitor the concentration of the dye. And how do you determine what this Y is going to be? The order of reaction with respect to the dye. You plot concentration versus time. You plot natural log versus time. And you plot 1 over concentration versus time. Whichever one shows up linear, that will tell you what the order of the reaction is. Okay? So we say that the order of the reaction here is pseudo Y order. Okay, why is it pseudo Y order? Because it's not really just dependent on the concentration of the dye. It also depends on the overall order is actually X plus Y, right? But since we're setting it up so X doesn't matter because it's lumped into the constant, the apparent rate constant, you say you have a pseudo. So if Y it turns out to be 2, then you say your reaction is pseudo second order. If Y turns out to be 1, you say your reaction is pseudo first order. And like I said, you can analyze the data here using the techniques we've learned earlier. And that's why we looked at that first. We looked at the simple cases first because this is a trick that we can use to simplify rate law, the things we look at in the lab, into simple rate laws that we talked about earlier. Okay? So let's take a look at this one. Let's say you run a reaction between X and Y and you form product Z. Let's say you carry out an experiment where first experiment, your concentration of X is 1 molar, initial concentration of Y is 0.0001. And in the second trial, you double the concentration of X, and your Y initial concentration is still 0.0001. So each individual trial, let's say trial 1 by itself, okay, will allow us to determine the reaction order with respect to reactant. Which reactant, A or X or Y? What would be the answer to that question? In fact, in other words, if you just ignore trial 2, okay, and just look at the data from trial 1, or ignore trial 1 and just look at the data from trial 2, can you determine the order of reaction with respect to one of these two reactants, and which one? Why? Okay, in the method of isolation, any given trial will allow you to determine the rate, the order of the reaction with respect to one of the reactants by flooding it with all the other reactants. This is excess. Throughout the reaction, your X is hardly going to change. What you'll actually be able to, the rate law for this one would be, okay, so rate for reaction 1, trial 1 would be equal to K times 1.0 raised to the power X times concentration of Y raised to the power, let's say Y. This whole thing right there would appear to be constant during that trial. That's an apparent constant. The trial will allow you to determine the order of the reaction with respect to the reactant that's present in small amount. Same thing with trial 2, except that in trial 2, what's your rate constant going to be? For your rate in trial 2, you'll also be able to determine the order of reaction with respect to Y. Your apparent rate constant is just going to be different. Okay, so you get a different apparent rate constant for the 2 runs. So that tells you then that these 2 runs will allow you to determine what? Allow you to determine X. Because the K apparent will be different. Okay, you're going to have different apparent rate constants for these 2 runs. So let's summarize what we do in the method of isolation. If R is your limiting reactant, okay, for any given run, the rate law is going to be equal, the rate is going to be equal to an apparent rate constant times the concentration of R raised to the power R. That you can determine, okay? And you can determine the apparent rate constant for that run. If S is your excess reactant, then your apparent rate constant for any given run is equal to the true K times the concentration of S raised to little s here, which is the order of reaction with respect to S. Okay? So you do at least 2 runs, different S values, same R. All right? So from that, you can determine your R for each run. And then what you do is you plug in the K apparent and the concentration of S for both runs, and that will allow you to determine the order of reaction with respect to S. You have 2 equations and 2 unknowns. So you have K app equals, so you have this one and this K and this S would be unknowns for each run. So if you do 2 of those runs, you'll have 2 equations and 2 unknowns. You can figure out the true K and the value of S. Right, so let's illustrate that. The apparent rate constant for the reactions of a dye with a hydroxide is shown below. Determine the true rate constant and the order of reaction with respect to hydroxide. So your apparent rate constant, okay, is just the true rate constant times the hydroxide raised to the power X. So for experiment 1, what's our apparent rate constant? Apparent rate constant is 2.00 per second equals the true K times, what's the hydroxide for experiment 1? 1.00 raised to the power X. For experiment number 2, what do we have? Our apparent rate constant is 8.00 per second. That's equal to the true rate constant And what's our concentration of hydroxide for experiment 2? 2.00 raised to the power x. Do I have enough information to get the value for k and x? Yeah, I do. I got two equations and two unknowns. So how do I solve for k and x here? Okay, I got equation 1 and equation 2. A quick way is to divide equation 2 by equation 1. Okay? So what's 8 divided by 2? 4, right? Let me rewrite that. So I have 8.00 per second over 2.00 per second equals k times 2.00 to the x divided by k times 1.00 to the x. What happens here? What is 8 divided by 2? That's 4. K cancels out, right? What is 2 over 1? 2 to the x over 1 to the x. What is a to the x over b to the x? That's just a over b to the x, right? So this is going to be 2.00 over 1.00 raised to the power x. So that gives you 4.00 equals 2.00 raised to the power x. What is x? You should be able to do this in your head. 2 squared will give you 4, right? But if these are not nice numbers, not easy numbers to look at, then you can just say log of 4 is equal to x times log of 2. And you can solve for x. Divide both sides by log of 2. So x equals log of 4.00 over log of 2.00, and you should get 2.